All right, time to look at chapter 9 in the dog's book. So I'm just going to go through a couple examples with you guys and then get you going as usual. So chapter 9, we're trying to solve an easier related problem. So instead of the complicated big problem, can we look at a smaller thing that's easier to look at? Okay. So the first example, from 1 to 100, we're supposed to add the sum of the first 100 whole numbers. And I've talked about this one with you before, and so see if you can remember it. You know, there's two ways to do this. One is brute force, right? You could take 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, and you'd eventually get there. But most likely, you would make a mistake because there's 100 calculations to make, and even if you're really good at adding numbers, you're probably going to mess one of them up. Even if you put them in a calculator, you're going to probably forget to put a character in there, and then it's going to be wrong. So Carl Friedrich Gauss, when he was in elementary school, found a simpler way to do this. You know, he didn't have a calculator, he just had a slate, and he thought, well, I don't want to sit there and add up 100 numbers. There's got to be a better way of doing this. So he looked at something smaller. He said, well, what if I look at the first and the last number? 1 and 100 adds up to 101. And he said, you know what? 2 and 99 add up to 101, and so do 3 and 98, etc. Well, then he said, if I pair these, first and last, there's 50 pairs because there was 100 numbers. And all of those pairs add up to 101. So if I take 50 times 101 and get 5,050, easier way. A lot less calculation, probably a lot better chance of being more accurate. Okay, so one way of looking at a smaller, more relatable one. Okay, how about this one? The clerk of Simpletown has the job of getting materials ready for the next municipal election. There are 29 issues and candidates. In the last election, there were 28,311 registered voters representing 18,954 households, and they voted at 14 polling places. In Simpletown, all registered voters vote in the election. The clerk figures she needs a proportional amount of materials for this new election. This time, there are 34,892 people registered to vote. How many polling places will be needed? Well, we can certainly set up proportions with the numbers we have, but one of the ways to look at a simpler related problem is to make the numbers easier to work with. So instead of 28,311, we could say let's look at 30,000. Instead of 18,954, maybe we look at 20,000. Okay, so if we list them kind of as a rounded, maybe rounded to the nearest 10,000 with the big numbers, we've got a little bit easier way to tackle this. Okay, so we know in the last election there were 15-ish polling places with 30,000 voters. Well, now if we have 35,000 voters, how many polling places we have? We can set up a pretty simple proportion for that, you guys. Okay, like so, and when we solve this, we get 17 and a half. Now we know that's not exactly right, but we didn't move our numbers around that much, so we're probably pretty sure we're going to be between 17 and 18. And if we want to err on the side of caution, we could go to 18 and we're probably going to be okay. So that's one way of looking at a smaller, more related problem. Similar numbers instead of the same, working with nicer things. Okay? How about this one? How many squares are there on a checkerboard? Think about that for a second. So we know that there's 64 of those little 1 by 1 squares, but if you allow things to overlap, there's a bunch of 2 by 2 squares and 3 by 3 squares and 4 by 4 squares, etc. Okay, so for this one, we're going to break it down into smaller problems, right? How many 1 by 1 squares are there? How many 2 by 2 squares? And maybe we'll find a pattern and it'll make our life easier. So if you draw out a checkerboard or use your graph paper to do it, you can go through and count some of these things. So 1 by 1 squares, we know there's 84. There's 8 rows, 8 columns. And it turns out 2 by 2, if you draw all those out there, there's 7 by 7 of those, 49. And then 3 by 3s, there's 36 when you draw them out. And at some point here, we're starting to recognize, I hope, that these are just perfect squares, right? This is 8 times 8, and then 7 times 7, and then 6 times 6. And as you would expect, 5 times 5, 4 times 4, 3 times 3, 2 times 2, etc. And we get all the way down to one big 8 by 8 square. Well, in the end, then, I just need to add these together. There's 204 squares on a checkerboard. But we broke it down into smaller problems. You know, let's look at the 1 by 1s, the 2 by 2s, the 3 by 3s. We eventually found a pattern with that so that we didn't have to count all of them. And then we could add them up. Okay, so pretty straightforward. All right, so that's all I've got for the first part. Thanks for checking in, and see you again tomorrow.